So we just looked at the linear function or the number plane, or I suppose we could call it Cartesian geometry. Now we're going to look at Euclidean geometry. Now, the main thing with Euclidean geometry is the deductive proofs, the setting out of the proofs and what have you. So let's just recap a few things. So some definitions. So different notation that we can use to, well, abbreviate, if you like. So we know that the two vertical lines we can write for is parallel to, the upside down T, perpendicular to, 3 horizontal, congruent to, 3 vertical, similar to, 3 dots forming a triangle, and this way is therefore. This one's not used as often, but if the triangle is the other way around, that's a shorthand notation for because. So some people like to do that when they're doing their reasons. They'll go, oh, because whatever reason. So terminology, produced. Okay? So when we draw a line or extend a line, the geometrical term for that is to produce the line. And the way we say it is important, because if someone's reading your proof, they need to be able to redraw your diagram. So here's an interval xy. We could say xy is produced to A. So that means the order goes x, y, through to A. As opposed to if I put it on the other side, then I would say yx is produced to B. Because whenever you're doing your proofs, the key thing with all your reasoning and logic is there's no ambiguity. Whatever you write down, it needs to be clear so that everyone reading it would understand it to mean the same thing. Foot, base or bottom, but it doesn't necessarily mean it has to be at the bottom of the picture. So B here is the foot of the perpendicular. So that's where the T meets. Collinear, well, we talked about that in Cartesian geometry, points that lie on the same line, and concurrent lines that go through the same point. Transversal, often seen when we're looking at those parallel line theorems, but a transversal is just any line that cuts another 2 or more lines. So that's what we call a transversal. Conventions, when we're naming shapes and angles and things like that. So angles and polygons we always name in cyclic order. So this one here I could call ABC, I could call it CBA. 2 different ways of noting. Some people like to put the angle symbol out the front. That's probably the most common way of doing it. Another way of doing it is putting the, what's that called? A caret, I think it's called. But anyway, that symbol above the vertex, and B being the vertex, that's where we put it. Now, if there's no ambiguity, then I could just simply call it angle B, in other words, the vertex. But that has to be when there's no ambiguity. If you have the vertically opposite angles, and if I was to just call that middle angle A, well, there's 4 possible angles I could be talking about. So in that case, I would name it A, B, C, or whatever it happens to be. There's a not cyclic, but there's a quadrilateral. Lots of different names I could call this, so long as I'm just going around in order. Clockwise, anti-clockwise, doesn't matter. So VP, QT, QP, VT, QT, VP, TVP, QP, QT, whatever. There's a whole heap of them you could call it. When we name our parallel lines, name them in corresponding order. So here I would say AB is parallel to CD. Or I could say BA is parallel to DC. Equal lines, well, we know that one, we just mark it with the same symbol to show that they're equal. Usually just a dash or 2 dashes if there's some others, 3 dashes if you want to go crazy, 4 dashes if you're bored, 5 dashes if you're... Anyway, however many, but if it's got the same number of dashes, it's the same length. So in that one, PQ is SR, PS is QR. All right, when you're constructing your proofs, any line you write down should be some piece of given information to you. Right? So don't assume things given to you though. So you might be told 2 sides of a triangle are equal. That doesn't mean you can say it's an isosceles triangle. You've got to prove it's an isosceles triangle. The information they've given you is 2 sides are equal. So you'd say, well, look, AB is equal to AC. Information was given to me. Therefore, it's an isosceles triangle because 2 sides are equal. It might be a construction of a new line or a new point or something like that. And you should be really clear. So again, whoever's reproducing your solution would put that point or that new line in exactly the same spot. A recognised geometrical theorem. It's not one that you've just made up. Right? It has to be a recognised geometrical theorem or assumption. And so the actual theorem I'm using needs to be stated either explicitly or in the actual working out itself. You notice what I've done here? I've done it both. I've said the theorem explicitly, in other words, angle sum of a triangle is equal to 180 degrees. So I've said exactly what the theorem says there. But I've also put it in my working out as well. I said, well, look, A plus 25 plus 120. So all three angles add up to 180. So whether it's in your reasoning or whether it's explicitly or you've written it in the actual working out itself, it needs to be there, what the theorem is. Reasoning, clear and concise. Okay, this is not English. We don't want essays. And of course, the last thing you could write down is anything that logically follows from other things you've already written down. It might be an addition of two lines together or something like that. All right, let's have a look at some angle theorems to start off with. And probably the first one where we look at is something like this, where we say angles in a straight line, they add up to 180 degrees. It's an interesting little theorem because there's lots of different ways I've seen people write down the reasoning for this. So if I had a question like this, there's x and there's 30. Yes, okay, if the question simply said find x and it didn't say give reasons, we'd just go, oh, well, x is 150. But if it's a proof, then I would do something like this. I'd say, well, look, x plus 30 is 180. That's the theorem I'm using. And I'm using the fact, I call it a straight angle rather than a straight line. But straight angles are 180 degrees. Okay? I've seen some people say, what is it? Adjacent supplementary angles. Have you seen that one? It's okay if there's only two angles. But if you had three angles on a straight line, you can't say adjacent supplementary angles because by definition, supplementary angles are two angles that add up to be 180. So I think that's why I prefer just writing a straight angle. Some people write straight line, yeah, but as long as we've got the idea of what theorem we're using there. And of course, there's our answer, 150. There's that vertically opposite angle one I was talking about. Vertically opposite angles are, of course, equal. So in this one, I'd go, well, 3x is 39. Vertically opposite angles are equal. So, of course, from that we get x is 13. Angles about a point. Angles about a point at 360. So I get that sort of question, and I want to work out what y is. Well, okay, they all add up to be 360. But similar to what I did with the straight angle, I say, well, this is a revolution angle. And a revolution adds up to 360. Y is 75. All right, the parallel line theorems. I know how you first were taught about the different types of angles, but when I was first taught about alternate angles, they said to me, oh, they're the Z ones. If you just look at the two angles, they form a Z. Might be a backward Z, but it'll be a Z. So in this case, you've got C and F, and you've got D and E. Why they're actually called alternate angles? Again, it's all to do with the transversal, and they alternate on the transversal. One's on the left side of the transversal, one's on the right side of the transversal. And that's where it gets its name from. Remember, there's two conditions. They are alternate angles, but also parallel lines. You can have alternate angles with lines that aren't parallel. They're just not equal. So it's the fact that the lines are parallel that makes the alternate angles equal. So you need both conditions there. If they're named, in this case I can't, of course, because there's no labelling. But yeah, if they were named, I would, yeah. Corresponding. Well, corresponding means in the same position. So in this case, we get four pairs. A and E are in the same position, but just on the different parallel lines. B and F are in the same position. C and G are in the same position. D and H are in the same position. So they're the corresponding ones. Co-interior, co, together, interior, inside. So they're together on the inside of the parallel lines. And they're on the same side of the transversal. So it's C and E. Of course, they're not equal. These are the ones that add up to 180. So you've got C and E and D and F. All right, let's have a look at a question, how I would set it out. So it's a typical sort of question. You've probably seen ones like it. I think I'll find x first of all. So I'll say, look, x plus 65 is 180. I've got myself a straight angle. And as you say, I'll name it if I've got the letters. So again, there's no mistake. I can direct people exactly to where I'm talking about. So CQD is 180. X is 115. Now, y. In order to do that, I need to construct a parallel line. I'm going to construct xy so that it's parallel to CD, and I want it to pass through P. So that's where we'll put it. So I've got XPQ going to be 65. Alternate angles are equal. I've got XPB plus 120 will be 180 co-interior angles. That gets me that XPB is 60. But angle BPQ is in fact those two angles added together. Now the reasoning I use for that is common angle. Because what I'm basically saying, look, it's the same angle. I'm just talking about it in two different ways. In one way, I'm talking about it as BPQ. And the other way, I'm saying, oh, it's actually these two next to each other. And subbing in, there we go, we get our 125. All right.